manual screen on.
Yeah. This is advanced tech right here.
Yeah. Connect the thing. Usually discharges quickly.
Oh yeah. It's
The power.
Yeah.
Is it? Oh, that's a different one, is it? Oh, I see.
Yeah, there you go.
Okay, yeah, no, that's good now.
Okay.
Does it have a zoom?
I'm not sure about that. Maybe. Do we need a zoom? Oh, okay, yeah.
I mean, it's probably okay in full screen.
Yeah.
Alright, so I want to start with a couple of announcements. I guess the serious announcement is that finally our setup seems to have stabilized. I can write on the slides and hopefully the streaming will work. Another thing is that homework 1 has been posted. Okay, so it's you can view it on the course homepage. It has like 5 problems. And yeah, it's due on 2 weeks from now, on Monday, September the 10th. Yeah, and I think some of you have submitted homework 0, around 40-50 of you, and they're being graded and they'll give some feedback in a couple of days. Okay. So, yeah, there were no major issues, but I think there were a few students who were probably not very familiar with the background, and I will probably write to those specifically. All right, so that's about the homeworks. All right, and okay. So yeah, so one thing about the homework 1 is that firstly you should start early, and the other thing is post comments and questions on Canvas, because that way everybody else will be able to see your questions. And many of you might have the same stuff, so it's good to post it on Canvas. And yeah, so unless the other thing to keep in mind is I expect all of you to at least argue intuitively why an algorithm is correct. So if I ask you to give an algorithm, you're expected to at least say why you expect it to be correct. Okay. So it doesn't have to be an extremely formal proof, but you should at least have some reasoning that about the correctness. And it's easier to just keep in mind 3 steps. If you're asked to describe an algorithm, you first describe the algorithm, then you argue about its correctness, and then you do some running time analysis. Okay, and running time analysis is usually worst case. Yeah.
Like pseudocode.
Yeah, it's great for description. Yeah. In fact, you should do pseudocode. Please don't do actual code.
Yeah.
Okay, so yeah, any other questions? Yeah.
Homework 0 is still available to challenges.
Yeah, so the question is if homework 0 can still be submitted. Yes, if you want, but just let us know that you have submitted so that we will actually take that into account. Okay? So, because I think the TAs just work through whatever is submitted right now. So, if you submit late, just let us know.
I thought that Tuesday on the homework
Was Sunday.
Yeah.
Was what? Sorry?
Is the homework different due date? Is really different with one?
Oh, it was supposed to be Sunday, but maybe maybe it was a day off.
Previously it was written 31st.
Ah, okay. Yeah, I mean that's fine. I mean it's homework 0. It's an optional homework, so it's so probably the dates were not matched. Yeah, that would be great. Yeah, okay.
Another question, sorry.
Yes.
So I missed the part where you're talking about pseudocode. What was that?
So the question was if it's okay to write pseudocode in when I say algorithm description, and so the point is that it's encouraged to write pseudocode. I said that don't actually write the code, write an intuitive description or give a pseudocode. Yeah. Okay, so sometimes even a pseudocode may be an overkill. So in which case, just a description would be fine. All right. Yeah, so I guess the main thing you've got to keep in mind is what if somebody who does not know anything about the course reads your answer, right? Will they be able to get something? Okay, so that's what you should keep in mind when describing the algorithm, and same with proof of correctness. All right. And okay, so what did we do last class? So last class we started off with a little bit of background about data structures, and I said that when you're thinking about data structures, there's essentially a few things you should keep asking, which is what kind of data does it store, what operations does it support, and what are like the time and space complexity of each of these operations. Okay, so these are like the basic things you should ask about a data structure. And one example we saw of that is this data structure called prefix trees. Okay, so it stores strings and it does a bunch of operations in time that's proportional to the length of the string that you're operating. And so in homework one of the questions deals with extending it in a pretty simple way. Okay, so in one of the things that we discussed in class about how you count prefixes. So you'll see a little bit more about prefix trees when you do the homework. Alright, and then we also saw another simple example of a graph algorithm for which we proved by induction why it was correct, and did a little bit of analysis on the running time as well. Okay, so this was about connectivity in graphs, which basically means you're given two vertices and you want to tell if there's a path. So this is what we did last class. Right, so today we're going to start with our first topic, okay, which is we'll talk a little bit about divide and conquer algorithms. Okay, so this is something many of you would have seen if you've taken an undergrad class, but we just want to review things a little bit so that everybody's on the same page, and we'll also talk a little bit about how you analyze divide and conquer algorithms, and often you analyze them by writing down what I call recurrence relations. Okay, so we'll see examples of that, and we'll see how you do this in a bit. Okay, so that's the goal for the day. Alright, so what is divide and conquer? Okay, so it's an old concept, right? Like people have been doing it for millennia, and so people have used it for not very good purposes. We will use it for solving computational problems. Okay, so hopefully more worthy goals. Okay, and so what's the main idea in divide and conquer? Right, so the main idea is you have a problem instance that on which you want to solve, okay? And the idea is to break up this problem instance into a bunch of subproblems. Okay? And how you do this breaking up will depend on the problem in question. Sometimes it's very naive, sometimes you have to put in more thought into how you divide this. Okay? But in any case, there is a divide step where you break the problem up into subpieces. Then you solve the subproblems. And sometimes maybe you need a little bit more information to solve these things, but that's fine. Imagine you can solve them, but the key thing is that you can solve them independent of the other pieces. Okay, like you solve these subproblems independent of the other problem. And now you combine all of these solutions into a solution for the original instance. Okay? So that's the basic paradigm. And how you do this divide step and the conquer step will keep differing from one problem to the other. So the main thing here is that the subproblems should not interact with one another. Okay, so that's the main. You should be able to solve the subproblem without knowing what the full instance was. Okay. All right. So this is the rough outline of what divide and conquer is. Okay, so yeah.
Sir, when you said that the subproblems should interact with each other,
yeah.
So do you mean that there should be no overlapping in the?
No, so they could actually have Right, this is a great question. So what he's asking is, so should the subproblems be disjoint? Okay, and the answer is no, they need not be disjoint, but it's just that solving one of the subproblems should not depend on the solution to the other guys. Okay, so in some sense, you should think of them as like individual problems of their own. So they may actually have some common things and so on, but that's fine. Right? So you should, but this process of solving one should not involve knowledge of the other. So that's the key. Okay, so that's a good question. All right, so let's see some examples of this. Okay, so but before we go there, you've got to ask, when does this kind of a paradigm apply? Right? So very often people use this divide and conquer strategy when somehow a problem naturally divides into smaller pieces. Okay? So there are a few problems for which it very effortlessly divides into not too many subproblems. Okay? Sometimes you have to put in more thought to how you divide this. And we also look for solutions to be kind of efficiently combined. Okay? So this combined step, how complex it is, often determines what the running time is. Okay, so this also you will see a little bit in your first homework. And and also when you're actually reasoning about algorithms, this divide and conquer type algorithms are very easy to reason about because often you can use an induction. Okay, so you can show by induction that that the algorithm actually works. And usually correctness proofs become easier. And complexity analyses are also usually by recurrences, which are just some mathematical procedures. Okay, so analysis is often quite easy for divide and conquer. All right, so this is just some meta statements about divide and conquer. All right, so let's start with a very simple example. Okay, and this hopefully most of you have seen this before. So you want to do sorting by divide and conquer. Okay, so what is the basic question? You've got some unsorted array A0 up to an minus 1. You want to reorder the elements so that in the end they are in increasing order. Okay, so this is the classic sorting problem. And if you want, you can think of like producing a new array out of it, which has the same elements as A, but they're in sorted order. Okay, so this is the basic sorting problem. Okay, so how would you solve this by divide and conquer if you had to solve it? Okay, so yeah.
Maybe the first step would be to find the smallest element.
Okay, so and then what?
So put it as the first element.
Yes. And so find smallest element. Sure. So you can do this, right? And you can recursively keep finding the smallest element. But this is not exactly divide and conquer, right? I mean, you are operating always on the whole array. You're finding the minimum element, doing something. But what if I told you, can you do something that's a bit more like breaking up the original problem into pieces? Right? So maybe you go first.
So this is kind of like merge, so where you break the array into two and two and two, and then you continually merge the arrays until they're sort of.
Alright, so this is a well-known process called merge sort, and hopefully most of you have seen it, but it's fine if you haven't seen it before. We'll see what it is. Okay, so the idea is very simple. You've got the array. It's A0, A1 to an minus 1. So what you do is you break up the array into a bunch of pieces. Okay, so you just literally follow this procedure, right? You had the whole problem instance, break it up into pieces, and try merging. Okay, so this is what you can try to do. Okay, so you've got A0, A1 to an minus 1. You break it up into, let's say, k pieces, each of size n over k. Okay, and now you solve the problem individually, right? So on each piece, what that means is you sort each of these things separately on their own. Then you somehow merge these solutions. Now the question we've got to ask is, how do you merge these solutions? Right? So let's see. So the divide step here is pretty clear, right? You just break this array up into disjoint pieces. Let's say you break it up into k pieces of n by k size each. And each one you just sort using a recursive procedure. Sort recursively. And now you want to merge. So how do you merge a bunch of sorted lists? So you've got a sorted version of the first chunk. So let me call this I want to introduce some notation, so I will call it B1, B2, B and by 3. And I will just have an index on the top saying that this is the first one. And then I have B1 of 3. Okay, so the superscript denotes which list it is. Okay, so this is the sorted version of the first group. Okay, so this is these guys. So these n over k elements. That's the first ones. The second ones are the next n by k. The last ones are the last n. Okay, and these are supposed to be in increasing order. Okay, so you've got this. And these are all in column. So let me write it more. Alright, so you've got a bunch of sorted lists. And now you want to come up with one list, the whole thing the whole thing should be sorted. Okay, and how would you do this process? Actually, anyway, I would prefer people who haven't seen merge sort before, if there is any. Okay, yeah.
Yeah, I haven't seen it, but it seems like you only need to check the first element in all these individual lists if you're going to be going in increasing order. So to take up to k, you have to look at up to k lists in order to get the first element. The second element you do the same.
Alright, so what he's suggesting is the smallest element in the combined array is basically one of the first elements of these. It has to be because it's the smallest element in the whole list, so it has to be the smallest element even in the sublist. Right? So you look at all the smallest, the first elements out here. Okay. And you look for the smallest of these guys, and this has to be the first element that you output in the entire array. So the observation is that smallest among B11, B12, so on to B14 is the smallest in the entire array. Okay. Can everyone read what I'm writing? Okay, so this is the smallest element in the entire. Okay, and this is this is what you do to get the first one. Right? What is the second smallest element in the entire array? How do you get that? Okay, so let's say this guy was the smallest in the first one. So you found this. Right? So this was the smallest element in the full array. Now how do you get the next one?
You check the first element in all the lists and the second element in the list that you found the smallest one in the first one.
Okay, so yeah, so what he's saying is the second smallest element must be one of these guys, right? So it's either one of the first elements out here, or it could be the second element in the list that had the minimum element, right? Because it's the second smallest in the full array. So it's if it is in that set, then it has to come after the smallest element. Otherwise, it has to be one of the first. So, in other words, or another more formal way of thinking about it is, you can pretend that this element was now removed, okay, and this is now gone, and now you just have the same problem again, right? You have a bunch of lists which are all sorted, and now you want the minimum element of that list, of whatever it is. Okay. So, and this is how you do it. So you just pretend that this element is now taken out, and now think of shifting this whole thing to the left, and now you have the same problem. So you have to look at the first elements of each of the lists that remain, and you just have to pick the smallest. Okay. So repeatedly do this, so the idea is. Smallest among these things. And now you shift let's call this the jth array. Shift the array B superscript j to the left and repeatedly. Now you just have to find the smallest element in the array with this guy removed. And this is how you do this. Alright? Pause for a minute so if you have questions. Yeah.
So I didn't get the notation exactly. So suppose we are dividing the entire array into n by k pieces, right? So suppose if the first piece is like, B1 is like 798.
And these sorted lists I'm denoting by these V superscript something. Right? So like so in this example, like the first list would be 3, 4, 5. The second list would be 7, 8, 9. And the last list would be 5, 6.
So suppose if we interchange B1 and B2 over here.
Yeah.
So B1 superscript.
So actually, what do you mean by interchange B1 and B2?
I mean if B2 is like 3, 4, 5. If
Okay.
we change the example. So my question was over the observation that the smallest among all of these would be.
No, the observation is just, suppose now I want to find what is the smallest element in the whole array. My claim is that if I look at these guys, the smallest element would be one of these elements. And this is obvious because take the smallest element in the whole array, it has to show up somewhere in these subarrays. Okay. And it has to be the smallest element even in that subarray. It's the smallest in the whole thing, therefore it has to be the first element. So that's that's all I'm saying. I'm not saying anything complicated. Right, so yeah, and now I look at these, I pick the smallest element. Now I pretend that I can just throw it out and pretend that this array is only 4, 5. Okay, so I'm kind of shifting this to the left and I'm doing the exact same operation. Each time I find the smallest. Yeah.
But over there you wrote it's like B1 superscript 1, B1 superscript 2. So it should be B1.
Yeah, that's my notation. Yeah. Because B1 superscript 1 is like the first element of that array. Okay. Yeah, that's just notation to simplify. I mean, yeah, so it's to formally write this thing. right? But what's going on is just something like this. Alright, so yeah, so this is the algorithm, right? And how do you analyze its complexity? What is the complexity of the merge step? Sorry? There's a bunch of answers. So, okay, but how does it depend on K? I mean, does it depend on K? Okay, yeah.
The number of comparisons that you have to perform.
Sure.
Find this-
And what is that?
That will depend on K. How many elements are there in each sublist?
So what would it be? I mean, I guess I'm asking for, yeah, I mean, essentially, what would be the number of comparisons or the time taken for this procedure? Right? So the procedure itself is this, right? So each time you find one element. And the one element you find is by comparing the first elements of each of these lists. And you find the smallest element at like the first element of these lists. And suppose it's the jth thing. Now you shift the jth list by one. And you can think of it as like removing this element from the jth list. Now you do perform the same operation again. Okay, so that is the algorithm. Right? Now, firstly, I guess to analyze it, what do you need to say, right? So you have to ask how many steps does this algorithm take, and what is the time complexity of each step. Okay, so what is the time complexity of each step? Let's take the first step. Okay, so it's K because, and why did you say that?
Because we have K lists, and so we have to compare K to different elements.
Okay, yeah, so you have K candidates for the smallest. You want to find the least of them, and this takes time K. Right, so each step takes time K. And how many steps do we have? Sorry? I heard N and I heard N over K. So which is the... Yeah, so we are doing this to find to find the entire order. Right? So you've got an array of size n, and each time you are outputting one thing at a time. Right? So you need n steps to output the whole array. So yeah, so you have n steps time for merging. So you have these n steps, each taking time.
So I have a question.
Yeah.
It's not and it should be not because I mean, as you go with it, say sometimes you might finish this first array and then K might become K minus 1. So
Okay.
so it should be like K times K equals N. I think
But that's also n.
it's N, but it's not those steps like so the one becomes K times N, the other one will go N. So
Yeah, that's a good question. So what he's saying is, suppose you run out of elements in an array, then you don't need k steps in the comparison. Right? So suppose you run out of one of the arrays, then all you have to do is compare the next k minus 1, and so on. Right? But if you think about it, that's a very special case. In general, you may have all the arrays showing up until the very end. Okay, so you could be extremely lucky, and you may run out of just the first array initially, then you may run out of the next, and so on. Even so, it's an exercise for you to determine what the runtime time will be. It will be something like n times k with some factor. Okay, but yeah, think about it. But in the worst case, it's clear that each time k different arrays will be there, and so this comparison takes time k. and you have to output n elements in the end. So yeah.
If you use the priority queue of the mins of each of the lists, could you get locking?
Yeah, so this is a good point. This used to be one, I think it was an exam question last year. So basically you could, instead of getting time k for the merge step, you can get time log k, because you could actually build a priority queue for the first elements. Instead of actually, and the main observation that he's making is that each time you remove you change only one of these arrays. Right? So yeah, you end up just shifting one of these things by one. So you can think of having some kind of a priority queue which just has the first elements. And what you're doing is removing the smallest element and replacing it with this guy. Okay. So yeah, if this is not clear, just think about it, and you can actually reduce this running time to something like log. Right, but it doesn't matter. So for now, let's think of it as k. So yeah, it turns out doing the log k doesn't actually buy you too much. Okay, so you can use larger arrays, but it doesn't buy you too much. All right, so this is the time needed for merge. So I will write it as O of n times k. But as he was saying, you can be a little bit smarter about it, and you can change it to n times log. Yeah.
Can you explain what is priority?
Yeah. So it's think of this binary search tree example that I mentioned last time. So it's a data structure that basically stores integers, and you can always find the min element in time. Okay, in a priority queue, you can find it in O of 1 time, but for this example, just think that you find it in log k time. Like it stores k elements, and the smallest of these k can be extracted in time, which is log k. And you can also remove it and add a new element in time log k. So it's a data structure for integers. And you basically, every deletion is log k, every addition is also log k. And finding the min is also O of log k. So if you're a bit smarter, you can do the finding the min in O of 1. That's what the priority queue does. But anyway, you have to remove it and add a new element. So it takes log k. So yeah. So any other questions? Yeah.
So the priority queue that you were talking about is basically a binary search tree that you were referring to.
Yeah, so there are many implementations of priority queues. So it's the one I'm thinking, you can use a binary search tree that would give log k for each operation. But there's a little bit something slightly smarter you can do, where finding the min element only takes constant time. Okay, the other two operations still take log k time. Okay, but just finding the min element is faster. Okay. And for our purposes, both are fine, because if you are willing to lose constants, because anyway, after finding the min element, you have to remove it and add a new element. Okay. So yeah. Okay, so is that clear? So the question was, what is special about a priority queue? Why don't you just use any binary search? So the difference between the two is only in this, how long the operation finding the min takes. Okay. Yeah.
But will building the priority queue also take time, because we have like n by k lists?
Oh yeah, this is a great question also. So he's asking, does building the priority queue takes time? What's the answer for this? Sure, it can be done in ON, but what is more fundamental about it? So note that the priority queue has to be built from scratch precisely once, right? So you've got these k lists, and there's the first step where you've got to insert all the k elements, k first element. After that, you're just adding one element and removing one element. Okay? So that's the main observation. Okay, so you've got to do this operation once, which takes k log k, because you've got k things that you're adding. And all the subsequent steps will only take log k. Okay. So yeah, so that's a good question. Right.
So we are doing some left shift of one specific array, right?
Yeah.
We compare, we add that to the time.
Yes, you've got to add to the time that you're taking. So again, so how long does a left shift take?
Depends on the elements in the specific array that we can be masked by
Can you do it? I mean, does it really have to be n by k? If you take n by k to do the shift, then you would really be in bad shape. Okay. But yeah.
Assuming you just have a bunch of numbers, you just need your number one.
Exactly. So the way you do this is you assume that each one is an array. You maintain a pointer which says where does this array begin, okay? And you just shift that to the right. Okay. So each shifting is just a constant time operator. Okay. But you're right. You have to take into account all of these times, right? So you have to account for every operation. So shifting takes only a constant time. Yeah, and I didn't write it because the k dominates that constant one that you have to do. So, alright. Anything else? Yeah, so these are all very good questions. So I'm happy that you've asked about. I think by now we've covered even all the details of this algorithm. I don't see any place where move something under the rug. Okay. So I think even the shifting operations take care of. Okay, so people usually do this by having queues for each of these things. A queue is just a data structure where you can easily like pop off the first element. Okay, and you just implement it by having a pointer that moves like this. So that's So this is how you merge. And again, so I just said that the time for merging is something like n times k. So what's the overall algorithm? You divide A into k pieces arbitrarily, each of size n over k. You sort each one recursively, and then you use this merge procedure to create a new sorted list. And this is the divide and conquer framework for this problem. It's very simple in this case. Okay, so what is the running time of this? You've got to do running time of each step, right? So, what is the running time of the first step? Sorry? Well, okay, in principle it's constant, but you've got to like create new arrays or something like this, right? So let's be very generous and say that the running time is O of n. In principle it could be O of k, but that's fine. So let's be very generous and give O of n, because we know that the last step takes O of n k. So this is what we just saw, right? That the merge step takes O of n k time, or n log k for a bit. So this is one of the things you should realize when you're doing analysis. Sometimes you don't want to be very precise about steps that don't matter. Okay, like the first step here can probably be done in time of k, okay, but I don't want to really bother about it because anyway the last step takes n times k. So, okay, and how long does it take to sort each one recursively? It depends, right? As of now, we don't know it. We have to do k procedures on arrays of size n over k. So since we don't know it, we can create some kind of a variable for it. Okay, so I'm going to introduce notation which says, so let t of n, or t of n, denote running time of procedures on an instance of size n. Alright, so suppose I create this notation, then I'm trying to analyze T of n, right? Because I'm trying to analyze how long the algorithm takes on an array of size n. Trying to analyze T of n. The first step takes that. What is now the second step in terms of this notation?
T of n over k.
Right, so each subproblem takes time T of n over k because it's an array, like sorting each one recursively takes time T of n over k. So it's like k arrays, each takes time to sort. Because this is a recursive call, you do the recursive call on each piece separately. Right? And each piece is of size n by k. Okay? So it takes time t of n by k. And you've got k of such function calls. Right? So it's like k arrays each time t of n. Okay, so the total time here is k times t of n. So this is so this is what this is. And now we've come up with an equation, right? So what we've come up with is that t of n equals k times t of n by k plus this k times n, which came from this procedure, plus this n from the first. Okay. So this is what we call a recurrence relation for this time complexity. Okay, so T of n is the time complexity of the problem, and we wrote T of n as k times T of n by k plus some. And this is what often happens in divide and conquer algorithms. There will be some size of the problem, which is usually denoted by n, and you will write the time taken on that instance as a combination of time taken on smaller instances. Okay, so in this case, there are k smaller instances, each of size n by k. Okay, so that's why you have this recurrence. So this is a perfectly true statement, but it's not clear what T of n is from this, right? Because you've got to know what T of n by k is. Okay, and what is T of n by k? If you use the same algorithm, it will be something in terms of T of n by k squared. Right? So this is the problem. Okay, so this is so we want a way to, in some sense, solve this recurrence and come up with a closed form solution. Okay, so the goal is so closed form solution just means some explicit function of possibly k. Okay, so this is what we want. Right? So we want to come up with this. And let's, for simplicity, think of k being 2. Okay, so you can think of what the general case will be in 1. But let's just think of k equals 2 from now. Okay, so you have this simple equation, T of n equals 2 times T of n by 2 plus 3n. So if you have something like this for every n, what can you say about T of n? Right? So this is the question we want to understand. The goal is, as I wrote, it's coming up with a closed form for this. Okay, so let us fix k equals 2. Right, so these are called, as I said, recurrence equations, recurrence relations. And we want to know how to solve them. Okay, so and solving them just means coming up with a closed form. Okay, so you have a few examples of this also in your homework. So one thing I want to ask is, okay, so what are general ways of solving these recurrences? Right, so are there, do you have to like literally solve it for every problem, or are there some general methods? That's what we want to understand. So let's do a small aside about how to solve recurrences, and I wanted to give like a few examples. So first off, the disclaimer is that there is no single way of solving all recurrences. Okay, so each one often takes a little bit of proving for itself. Okay, so there's no silver bullet. There are theorems that handle a bunch of general cases that you are likely to encounter, but there's no like single theorem that does everything. So that's this. So the first method that works well if you are good at it is you guess the solution and you prove it by induction. Okay, so like for instance here, suppose I guess that T of n is less than or equal to n to the 1.1. Okay. Turns out we can prove this by induction. Okay, so if you think about it a little bit, if this is true for n by 2, it's also true for n. I mean, you can verify this by just expanding that expression on the right and so on. So this is a simple example. Yeah, so you can guess and you can prove by induction. Okay, so this is one way you can solve recurrences. And people guess by different means. One is, some people plot things and see how this function is growing, try to guess at it, and then just prove by induction. And sometimes you guess something, you try proving, then you realize that, oh, okay, the proof doesn't go through, and I need to change my guess. Okay, so that's something that also works. And yeah, so this is a good method if you know what the right answer is. Okay, so yeah. And there's this other method which, yeah, these guys, Lehman and Layton, have a nice name for it. It's called plug and chug, which is basically you have the recurrence, you just expand it out and hope for the best, right? So you just keep expanding it, and hopefully you'll see a pattern. And from that you can probably guess, and then you can go back to step 1. Okay, so this is called this. So the idea is keep plugging back into the equation. I'll show you how to do this for this example. And see a pattern and prove by that. Okay, so this turns out to be a pretty powerful thing. Okay, so many recurrences you can actually keep expanding and see where it's going, and in some sense you can, and you can guess what the answer should be. So there's a third method which I often recommend using, which is basically you just write down the recurrence tree. I'll explain that in a little bit, and and you can try to do some systematic computation of what exactly is going on. Okay, so we'll see an example of this. So it's called a recurrence tree. So this doesn't always work, but it works in many cases. So alright, so let's see how you solve this very simple example. Okay, so let's do the first, like the second thing. Okay, so the first one is just guess, and I don't want to spend too much time on that. Okay, so let's do this. Right? So what's going on here? What does this mean? So I can write. So let's, for simplicity, write this as 3n plus 2p. Right? What does it mean to now do this? Right? So I can write t of n now as 3n plus 2 times, plugging in the same expansion for t of n by 2. Right? So what would I get there? Okay, so again, I'm writing the n part first. So let's write 3 times n by 2 plus 2 p of n by 4. Okay. So this one, if I simplify this, so the 2 cancels out with this. Okay. So I get 3 times n plus 3n plus 2 not a cancel, so 4 times p of n by 4. Okay. So now I can ask, what is 4 times p of n by 4? Okay, so this guy I can now write as 3n plus 2n plus 4 times 3 times n by 4 plus 2 n by 3. And this one is, now I've got 3n terms plus 8 times p of n by 8. So now you can see some pattern, right? You're starting to see a pattern. If you don't see it, expand once more and you'll start seeing it. Okay, so what you will observe is that if I went on like this for some r steps, in each step, I'm adding one 3n term to the sum. Okay? So I would add, so this would be r times 3n plus, what would be the term that shows up over there? Okay, so it's 2 to the r times p of n divided by 2. Okay, and I can keep doing this. Okay, and until what r should I do it? Okay, so you've got to do it until this term becomes really tiny, that you get to some base case, right? So when you have a recurrence like this, the other thing you've got to ask is what is the base case, right? Because I always have t of n in terms of t of n by 2, right? So at some point the recursion should stop, right? So there should always be a base case. In this case, you can think of the base case as just being n equals 1. So n equals 1. Of 1. Okay, so it's like sorting an element, just a single element, where you just return it. So that's the base case here. So I've got to go until the base case, where n by 2 to the r becomes equal to 1. So base case is when n by 2 equals 1, and this is equivalent to r being log n to the base. It's just definition of the logarithm. So 2 to the r is n, so r is log n to the base 2. And that's it, right? So now you've got, if you set r to be equal to this, then this expression simplifies to 3n log n base 2 plus, what is 2 to the r? Log n, right? Because n by 2 to the r is 1, so 2 to the r is n. And plus n times, what is t of n by 2 to the r? It's t of 1, it's just 1. That's t of 1. So this is it, right? So now you've got a closed form for this whole thing. Okay, so you basically have t of n equals 3n log n 2 plus 1. So there's a little bit of subtlety here. What if n is not a power of 2 and so on? Okay, but I'll leave you guys to think about these kind of things. Okay, so they're not serious. So you'll add a small constant to the 3n. So yeah, but any questions on the overall thing? I think a few people seem confused by the base case, so maybe I'll wait for a question. Did you have a question?
So in the techniques that you discussed, by finding out the recurrence,
Yeah.
so do all of these give a tight form and the runtime?
Yeah, so this is another good question. So what he's asking is, do all of these methods, right? So I've discussed a bunch of methods, right? Do all of them give exactly the right answer in terms of like, is there an upper and lower bound, or is it just an upper bound, right? So very often the guess is usually just an upper bound. Okay? So if you want, you can actually guess the right bound and try to show both the upper and lower parts of it, both by induction. Okay, but very often you care only about the upper bound. So for instance, this n to the 1.1 that I mentioned is not a tight bound, right? Because we just saw that there is also a bound, that the actual expression is 3 times n log n. Okay, so n to the 1.1 is a strict upper bound. So very often the guessing just gives, it gives some upper bound. Okay. And so these two, when they work, they often give you the right bounds. Okay, because that's presumably how you will end up reducing these. But sometimes this plug and chug becomes too messy. Okay, and you may want to just start approximating things. In which case you will only get upper bound. So there's a homework exercise where I think the plug and chug becomes messy if you try to do it that way. Okay, so there you may want to guess what the bound is and use some upper bound. Alright, so
Why t of 1 is 1?
So that's specific to this problem, right? So what is t of n? It's the amount of time taken to sort an array of length n. So t of 1, you just have to return the same thing. So it takes this constant time. I'm just writing it as 1. Right. So anything else? Yeah.
So you mentioned that if in this case k is more than 2, that equation will have what? That term will have one constant. One constant.
Yeah, so if k is more than 2, you would have something like this, right? So for instance, if k is 4, you would have t of n is 4 times t of n by 4 plus 5n. And you can try to work out what happens in this case. So it will be a calculation very similar to this. You will get log n, but with n log n with a different constant. So you can see where this will show up, right? Like this 3n term is now replaced with the 5n. That's kind of right. Alright, so I want to also mention the second method, which is often useful. Right? So here, let's start with the same recurrence. So this works when you have clean integers, okay, which you often have. Okay, so the reason I call it a tree is because it's easiest to think of it as a tree. So you want to compute what t of n is. So in some sense, this is a pictorial way of doing plug and chug. Okay, so that's one way to think about it. So you want to compute t of n. You know that it's 2 times t of n by 2. So you've got 2 subtrees of t of n by 2, and you've got this 3n term that's off on the side. So this is, if you think of what happens in your recursive procedure, it's like in the first level of recurrence, this is what's going on, right? You have an instance of size n, it's breaking up into 2 instances of size t of n by 2, and you're doing an extra work, which is like 3n. Okay, so this is, I call this the extra work that you're doing there. Yeah, this is also kind of the actual work at this recursive step. And now you recurse, so t of n by 2 again breaks up into these things. So you have t of n by 4, t of n by 4. And you have this extra work now, which is 3 times n by 2. And this is the stuff that you track of. You have the same thing. And you can write down this tree. Okay, so you can see how this is going. Right? So you have some extra work in each leaf. And the total running time of the algorithm is can be found by first adding up all the extra works at each level plus whatever time it takes to compute the leaf, to compute the answer for the leaves. Right? In this case, the leaves are basically a whole bunch of T of 1s. Okay. And you also have some extra work. So yeah, so I won't go into too much detail because it's, if you think about it, it's exactly the same equation that I wrote earlier, but it's just a more pictorial way of seeing this. Okay, so what you've got to do is figure out what extra work you are doing in each layer. And in this example, you'll see that in this layer you have 2 of these n by 2 steps. So the extra work in this layer is something like 3n. Total extra work is 3n. And in this level you will have 4 terms that are all 3 times n by 4. So in this layer also the total extra work will be 3n, and so on. And in the final layer you'll have a bunch of T of 1 terms. How many T of 1 terms will you have? And yeah, so it turns out you'll have exactly n because there's 2 T of n by 2s, there are 4 T of n by 4s, there are 8 T of n by 8s, and so on. And in the end, you have n T of 1s. Okay, so, yeah, sorry if it was a bit fast, but it's something very simple. So I'm just. So we have 2 such terms. You have 4 terms that are like this. And yeah, in general, you have 2 to the r terms that are of the kind n by 2 to the r. And again, for r equals log n, that's like saying that there are n terms that are like p of 1. And here you are just returning the answer. So this is also this is some work that you're doing. So the total amount of work, you get the exact same answer this way also. So you get an extra work of 3n in every layer, and you have log n to the base 2 layers, and so you get the exact same answer. So you get 3n log n to the base 2 plus n times. So yeah, this is a pictorial way of doing the same calculation. And the thing you've got to remember here is that you've got to keep track of what actual work you're doing in each layer, and you've got to add that. And this is how you are. So I'll show you another example of this. So yeah, so let's keep going. Okay, so I want to do, actually see a couple of examples. Okay, so this, all of this was for sorting. Okay, so now let's see a slightly more involved example, which is that of multiplying integers. Okay, so what is the problem here? You are given 2 n-digit numbers. Okay, so let's call this, let's call these A1, A2, AN times B1. So there are n digits in each of these numbers. Okay, so those are the numbers, and you want to multiply them. Okay, so how many digits will the product have? Just a sanity check. Sorry?
Up to twice n.
Yeah, so it'll have up to twice n, and that's just because, I mean, you know, that's something easy to check. Okay. And yeah, so this will have up to 2 times n. Okay, and now how do you multiply these? So we all know the algorithm from high school, right? So you write down those numbers and you multiply digit by digit. Okay, and So it works like this. As an example, I got from somewhere. Okay, so you at least you have these shifts and then you add them up. So this is the basic high school algorithm, right? Not even high school, maybe like elementary school algorithm. Okay, so what is the running time of this? So note that this is an algorithm, right? Like I can multiply any two numbers using this procedure. So what would be the running time of this? Okay, so why is it n squared?
Because you're multiplying every number by another number.
Okay, so what he's saying is n squared because look at this procedure, right? At least this table is of size n squared, right? Because you will have bn multiplying these guys, and multiplying one digit by one digit, you can assume it's a constant time operation. There is a carry, and adding that is also one constant time operation. And you keep doing this, and you take time n to come up with something of this kind. You take time n to come up with something of this kind, and so on. So coming up with this sequence of numbers takes you something like n squared. Now you've got to add them up. Okay? And adding, if you think about it, it's like adding these numbers with zeros, right? So that's basically the idea behind this algorithm. And now you have n numbers, each with at most 2n digits, and you want to add them up. And there are many ways you can do this. You can just think of adding these two and then adding the sum to this and so on. So you realize that the whole thing can be done in something like n squared time. Okay, because it's addition time. Trying to create this table, which is basically this set of numbers plus time to add. And each is like n squared. So the whole thing takes time roughly. Okay, so this is very simple. Yeah, you can think about this. All right. So the question is, can you do better? Right. So can you do something which is better than this naive elementary school algorithm? So how many of you have seen better ways of doing it? So what have maybe a little less than half. All right. So yeah. So we'll see an algorithm that's based on divide and conquer. And we'll see how you can beat this naive n squared upper. So that will be the goal, right? So firstly, how would you do divide and conquer on a problem like this, right? Because you're given two n-digit numbers, and you want to figure out how to multiply them. Right? So how would you do divide and conquer for? In some sense, you want to break up the problem into subproblems, right? What would be a reasonable way to break up this multiplication problem into subproblems?
Multiply by units of 10, units of hundreds.
Okay, so that's right. So that's just restating the problem, right? I mean, in some sense, you're just expanding out this a1, a2 to an as an plus 10 times an minus 1, 100 times a. Yeah.
N as n by 2 is
Sure. I think what he's saying is break these numbers up into two chunks, right? So you have n digits in each of these numbers. Try to break this up into two numbers. Okay, so let's call them x. This is y. This is z, and this is w. So each of these is an n by 2 digit number. Okay. And somehow you want to multiply these guys to find the overall product. So is there a way of doing this? I mean, clearly you can't just multiply these individual things and do something, right? Like, what do you have to do? Right, so let's call this whole number A and this whole number B. So we want to make intuitive sense of what it means to break up a number into two chunks. Right? So it seems like a reasonable thing to do if you want to do divide and conquer. Right? So you've got a bunch of things, you break it up into chunks. Right? So how do you, for starters, for instance, can you write A in terms of x and y?
So it's like x followed by the number of zeros that y, the size of y.
Yeah, so what he's saying is A, I can write it as x appended with n by 2 zeros plus y. Right, so this is clearly true because x is a number, so this whole thing is an n digit number. But I've just replaced all the y digits by 0. Then I'm adding 1. And this summation is clearly the same as A because all the zeros get now updated to the digits of 1. So this is this is something which is easy to see. Okay, so this I can also write it as x times 10 to the n by 2 plus y. Because what is the number that is basically x appended with n by 2 zeros? It's x times, so for instance, if I take 5 and append 2 zeros to it, I can write it as 5 times 10. It's just by definition. Right? That's what appending zeros means, right? You're multiplying by 10. So, yeah, it depends on the base. Like if you're in binary, then you have to write 2 to the n by 10. But since we are in base 10, you assume that you write 10 to the n. So that's A. And you can do the same for B. Okay, so you can write B as z times 10 to the n by 2 plus w. Okay, so now you are ready to write A times B as something in terms of these x, y, z, w. Right? Because now you can say, okay, so I have this is an expression for A, this is an expression for B. So A times B, it's this term times this term. And so that's basically xz times 10 to the n plus xw plus y times 10. So here I'm just doing something, it's just pure arithmetic, right? I'm just multiplying these two terms, and this is what I get. Now, right, so suppose I had this, I had the values for 4 of these things. Now how do I find the product A times B? So let's say I've computed this, and this I can hope to do, right? Because each one is an n by 2 digit number. and I could use a recursive procedure to compute. And now I just have to do this operation. So if I have the values for these individual terms, how long does it take to compute this expression on the right? Any guesses? Actually, if I had xz, how long does it take to compute this thing? Yeah.
Assuming we plus some kind of dipshit operator to do dipshit, that it's pretty darn fast.
Yeah, so this is pretty quick, right? Basically, if I have xz, if I have what the answer to x times z, and I have xz times 10 to the n, I'm just adding n zeros on the right. So I can come up with the number, with this number, in just linear time. So it's just time n. If I have these two guys, I can definitely compute, each of them I know is an n-digit number at most, because x and w are n by 2 digit each. So the product is at most n digits. And so this is n digits, that's n digits. Adding them takes time of n, because I just have to add digit by digit. Okay, so this thing, and now I have to shift by n by 2 position. Okay, so that's that. And so each of these takes time n. Of n. And this guy is, and now you have to add these two n-digit numbers, which again is only O. Okay, so if I had the answers to all of these computations, then the combining step, okay, so the combining step is only O of n. The conquer is O of n. Because, right, I'm just doing this addition. Alright, so what is an overall recurrence for this? If I denote by t of n the time to multiply two n-digit numbers, I'm saying that t of n is time for breaking up, which is clearly O of n, time for combining, which is O of n, plus time for all these recursive calls. So how many recursive calls do we have? Sorry? 4. Yeah, so the naive way of doing it, you have 4, right? Like you want to compute this, you want to compute these two, and you want to compute the last two. Okay. So you've got t of n is 4t of n by 2 plus 4. Okay, so this is the recurrence you would run for this algorithm. So you would compute these multiples, and then you would combine them using this expression. Okay, so this is what. Right, so maybe I'll pause for. Yeah, we're almost out of time, so maybe I will just show you how to solve this recurrence and then so I'll assume that you guys agree with this recurrence, and we'll see that it's not gaining us much, right? So you get t of n equals 4 times t of n by 2 plus O of n. So let's give some constant to this. Instead of O of n everywhere, let's write it as some c times n. Yeah, O of n basically means some constant times n. So let's write it as c. So now you've got this kind of an expression. And so now if you do this plug and chug type method, you basically get t of n equals 4 times, okay, let's do it the way we did earlier. So you get c times n. And this is c plus 4 times plus this you observe is like can expand again. So this is Cn plus 2Cn squared and C. Sorry, n by 8. Okay, and right, so you can do this, right? So what you will observe is that after R steps, you will get Cn plus 2Cn plus 2 squared Cn plus something like 2 to the R 1 times Cn plus 4 to the R times E of n by 2. Okay, so if you think about this, but this is what you can observe as a pattern. Okay? So you can also draw the recursion tree in this case and see that each time, in some sense, the tree has 4 subchildren, but each one is only, each one reduces this only a factor 2. Okay, so the n reduces by factor 2, but you have 4 subchildren. So earlier the n was reducing by a factor 2, but you had only 2 subchildren. Okay, so yeah, so this is what you get, and it turns out that if you solve this, if you do the same thing, put n equals 2 to the r, put that is r equals log n to the base 2, then this term, it turns out becomes something like 4 to the r times r minus 1 times t of 1. 4 to the r is 2 to the r whole square divided by 2. Okay. Yeah. So this is all basic arithmetic. So I will let you guys do it. Also, you can see the notes. Which, from this lecture on, I can add notes because the previous stuff was like basic. So yeah. So you'll see that this is this, and this will actually be n squared. Okay. So you haven't gained too much from doing this. Okay, so you came up with a clean, divided conquer way of doing things, but it did not gain. So next time you see how you can actually do it. So that you actually yeah.